I'm talking about the difference between MISR and CERES TOA shortwave flux data. And while CERES is flux is relatively a direct measurement, one of the major differences with MISR is that MISR broadband albedo is a converted quantity from 4 narrowband albedos, and those are regressed onto CERES broadband albedo. So we used the MISR broadband albedo product, then converted it to the flux by multiplying incoming solar insolation. MISR provides 3 different types of albedos, and MISR's arrangement of 9 cameras provides good coverage of zenith angle. And the local albedo only accounts for top leaving BRF bidirectional reflectance factor over 2.2 kilometer region, and restrictive albedo accounts for top and side contributions over 35 kilometer domain. And expansive albedo has a viewpoint at 30 kilometer height. It accounts for all the areas expanding a few hundred kilometers for integration. So in this presentation, we used a restrictive albedo product because it can be a more useful measure of scene-dependent properties, and it is analogous to the CERES determination of TOA albedo from a single view. The comparison of PDFs of global all-sky monthly broadband TOA shortwave flux during the Terra measurement from 2000 to 2020 clearly shows that 3 PDFs from MISR, CERES, and MERA2 are deviated from normal distribution. The distribution is asymmetric from the maximum population with positive skewness, which means there are more data on the right side of the maximum population. In this presentation, when I mention global, global means from 80 south to 80 north, since MISR does not cover the latitudes beyond 80 degrees. They commonly have measure one peak near 60 watts per meter square, but MISR value is about 7 watts per meter square, less than that of CERES. On the right figure, all 4 of MISR spectral shortwave flux are showing similar positive skewness. So we can see that this feature is caused by nature, not by the outliers of the measurement artifacts. This is a schematic of MISR shortwave flux PDF with 2 hypothetical normal distribution curves. The red curve is a normal distribution with the same mean and standard deviation of the MISR shortwave flux, and the yellow curve is a hypothetical normal curve with the mean at the maximum population of the flux. And those 2 curves are mimicking the global distribution of shortwave flux over ocean and land. So what are the implications of non-Gaussian distribution? Gaussian or normal distribution is a distribution of random variable, and the PDF is symmetric on either side from the mean. So mean, median, and maximum population are all aligned together. In fact, the normality of the distribution is one of the underlying assumptions in data analysis. In practice, however, the TOA shortwave distributions are deviated from the normal distribution. They are not well characterized by the mean and standard deviation. Because the mean is greater than the median value, and it can overweight the average values. Another implication is related with high flux values above 300 watt per meter square in right tail, which represent Arctic and Antarctic high reflectance snow and ice covered area. With extreme hemispheric asymmetry, the reflected flux is difficult to be characterized over these regions, and besides, the shape of the distribution may not be preserving over high latitude area. So let us look at the difference between the mean and median, skewness and kurtosis maps from MISR and CERES. And I will get back to the high latitude regions later in the talk as time permits. We generated a climatology for MISR and CERES TOA shortwave flux by taking not only the monthly mean averages, but also taking median values of shortwave flux at each grid for 20 years, and took the difference between the mean and the median. So two observations show very similar coherent patterns. Where are the most skewed regions? The difference between mean and median is outstanding over the Deccan Peninsula. The PDFs are shown for MISR CERES and also CERES all sky cases. And the PDFs are shown that all sky shortwave show long tails due to strong monsoon of this area. The skewness map has a maximum in Central Pacific, and the PDFs over this region show sharp peaks in both observations with high kurtosis. So when we look at more closely on this region, the most skewed region over the Central Pacific is located at the substance region between ITCZ and SPCZ, where the cloud fraction is relatively low and where the shortwave absolute values are less than 60 watts per meter square. The black contour lines here indicate 60 watts per meter square shortwave line. And the skewness and the shortwave absolute values are negatively correlated, and the skewness abruptly increases when the shortwave flux is less than 60 watts per meter square in both observations. So we know that cloud largely controls the shortwave distribution. Actually, cloud contributes to reduce the skewness by reflecting light in random directions. The complexity of the annual cycle of shortwave flux is evident from the hemispheric asymmetry of the solar insolation. The amplitude of the global mean solar insolation is 1 magnitude smaller than that of each hemispheric values. So as I mentioned earlier from the schematic, the climatology of the shortwave flux can be affected by the skewness of the distribution. Shown here, the figures are annual cycles of global mean and median for global, northern hemisphere and southern hemisphere, and also for land and ocean. The field marks represent median values of the flux, and on-field marks represent mean of the fluxes. Most of the cases, the mean values are higher than median values. So after repeating averaging the fluxes by taking means from zonal mean, latitudinal mean, and timely mean, the differences of the area weighted global mean from the median values, the difference is about 3 watts per meter square. They are common in both observations due to the overweighted mean, which is originated from the skewness. The large amplitude of annual cycle over the Southern Ocean can be attributed to the reflection from mid-latitude clouds over the storm track during the austral winter. So changes by cloud scattering dominates the changes in surface scattering over this region. This time we can look at the difference map as CERES minus MISR to see where they are most different. In general, MISR shortwave is a few percent lower than the CERES, and the stripes are from MISR narrow swath sampling. Differences were found over a high cloud region and also a high elevated region, and the cloud height is taken from CERES SSF product. We know that clouds dominate the atmospheric scattering contribution through a combination of cloud amount and intrinsic properties that define the reflectance of clouds themselves. So when we compare the low elevation and low cloud cases with high elevation and the high cloud cases, the difference between the two measurements is high for high elevation and high cloud cases. This difference may be attributed to different treatments between MISR and CERES for the radiance anisotropy of high cloud scenes. For a closer look, we classified the shortwave flux over ocean with different cloud height from 1 to 12 kilometers. It is interesting that the difference between MISR and CERES increases with cloud height, and some of the difference may be attributed to errors in treatment of 3D effects in the high cloud scenes. The PDFs are getting closer to the normal distribution for high cloud regions, and the skewness approaches to 0 when the clouds are located at 9 to 11 kilometers, as you can see from the plots on the right side of different percent and skewness as a function of cloud height. So this time, let's move on to Antarctic. You can imagine the complexity and difficulties of the shortwave measurement over the Antarctic, and differences between two measurements are outstanding in Antarctica. The comparison of the two measurement fluxes are well aligned with offsets in global sense, but over the Antarctic during the month of January, high albedo season, the two observations are off from 1-to-1 slope, and CERES flux tends to be saturated near 350 watts per meter square. So PDFs are confirming that the shape of the distribution is quite different between two fluxes, and the MISR flux comparison between the first 5 years and the last 5 years shows that the shape in the right tail is shifted due to snow melt, and the mean was also shifted, but the left side of the distribution has not been changed much. So this is different from the case of normal distribution, which the whole PDF moves with the mean. Besides, we can see that the skewness is the opposite sign of the global distribution, and the shape of the PDF is not preserving with long-term environmental changes. So as a summary, I'd like to throw a couple of questions rather than answers. The difference between MISR and CERES shortwave flux is large at high elevation and high cloud region, and should the PDFs be considered with caution in averaging TOA shortwave flux? And then which value can well represent TOA shortwave flux? And PDFs may not be preserved, but can change with time and location. And is there some potential in MISR spectral albedo retrieval over Arctic and Antarctic beyond 80 degrees? Because they may be quite useful. Thank you so much.